Good morning, everyone. So, we will be looking into the, as we have discussed in the last class, we are looking into the application of contraction mapping in chemical engineering processes. So, we have seen that contraction mapping is a very useful tool to obtain the uniqueness of a steady state that is occurring in the system. And probably in the last class I discussed about the importance of the steady state, that is in chemical engineering. So, I would like to reiterate once again that in any chemical engineering system the output is the most important product, and the product quality is the extremely important because it has a fixed and it has a tremendous market value. If we will be able to produce the output product to the required quality, then we will be able to market it appropriately. If it does not corroborate the required quality or the properties, then the whole batch will be waste. So, it will be there will be tremendous loss in running the whole experiment, because the most of the chemical engineering system they are producing materials of high volumes. So, therefore, you need to have a steady state by which around which the product will be produced to a desirable quality, and that steady state must be a unique steady state. Otherwise, for the same set of operating condition, if you have multiple steady state, then you may be landing up with a different steady state. So, that where the product quality may be different, may be beyond the bracket of the desirable quality parameters. So, therefore, it is very important to run the process in a steady state, and that steady state has to be unique steady state. But in order to have a unique steady state, you must be having a good control over the operating parameters, and there exists a definite relationship of the operating conditions where the steady state will be a unique steady state. Contraction mapping is a tool to identify the relationship between the operating parameters. In most of the cases, they are appearing as non-dimensional parameters whenever you will be writing a mathematical model to describe the system. Now, this combination of these parameters, there will be a definite relationship between these parameters, which will be dictating whether the unique steady state exists or not. Contraction mapping gives us a method or a tool to determine the combination of the operating parameters, the relationship between them. So, in the last class we have formulated the basic theory of contraction mapping, how it has been formulated, and the proof of the mathematical treatment of the idea that we have already we already considered. And in one of the in the fag end of the last class, we have taken up a particular example to apply the contraction mapping in order to determine the unique steady state. Now, in this class we will start with some more realistic chemical engineering system where the contraction mapping is of it will be utilized to determine the unique steady states, and I will be considering a case of a chemical reactor where the fermentation is going on to determine the unique steady state. So, the first example will be a case of chemical reactor. We consider an enzyme catalyzed. This will be one of the most vivid example where the contraction mapping will be utilized to obtain the condition on the operating parameters to get the unique steady state by using contraction mapping. So, it is very important to follow up this example to every detail. Consider enzyme catalyzed enzyme consider a catalyzed by enzyme catalyzed fermentation process. The kinetics of the process is governed by monod kinetics the reaction occurs in a CSTR. So, we have talked about CSTR in the last class. It is a continuous start tank reactor where the reactor is being started all the time and the feed comes into the system and goes out of the system. Since the reaction volume is appropriately stirred, it is assumed that the properties, the concentration and temperature in the reactor volume is uniform throughout, and it is expected that whenever you will be drawing a product out of it, it will be having the same concentration and temperature that is existing inside the reactor. So, that is the that is the principle of continuous start tank reactor. The reaction occurs in a CSTR with volume V and flow rate Q. The feed concentration of reactant S is CF and reaction occurs isothermally and it is an irreversible reaction. The reaction is something like this. The substrate, the monomer, the reactant gives the product with a rate constant. Okay, this is not rate constant K1 because it is a complicated monod kinetics, and the rate expression is given as minus R A is equal to K1 C divided by 1 plus K2 times C. So, therefore, if this is the system, now the questions are show the parameters. Parameters are the combination of values of the operating conditions. Parameters of these systems are dA, that is called Damkohlen number K1 V by Q, sigma K2 times CF, and we have to show that in order to have unique steady state, this relationship should be, the relationship of the parameters should be existing. Sigma must be lying between 4 and infinity, and Damkohlen number should be greater than 0.5 sigma minus 2 plus minus under root sigma square minus 4 sigma with minimum Damkohlen number is 1. So, that is the minimum Damkohlen number. The parameters, two parameters, Damkohlen number and sigma, they are basically the combination of the operating conditions. Damkohlen number is multiplied by K1. K1 is basically one of the constant in the monod kinetics. V is the volume of the reactor, Q is the flow rate. Now, volume of the reaction of the reactor and Q, the flow rate by which it is getting into the system, these are under our control. So, these are the typical operating conditions. So, we can have a selection on this. Similarly, K2 times CF, K2 may not be, we may not be tuning for a particular reaction because it is fixed by the reaction kinetics, but feed concentration is in our control sheet. So, it is one of the major operating conditions. So, therefore, these two parameters Damkohler non-dimensional parameters Damkohler number and sigma must be obeying this relationship, that sigma must be lying between 4 and infinity and dA has to be greater than this value. So, in order to have a unique steady state for this particular problem. Now, let us look into the solution of this problem. The solution goes like this. First, we write a material balance, species balance equation. It is basically reactant balance equation at the steady state. So, again if you remember in the last class, probably we have developed that for any balance equation we write rate of accumulation should be is equal to rate of in minus rate out plus rate of generation minus rate of consumption. Therefore, so this general equation of balance equation is valid for every quantity. It may be a species balance, may be a concentration balance, may be a mass balance, that means mass accumulated in the system is equal to rate of mass going into the system minus rate of mass that is coming out of the system, rate of mass that is generated into the system and rate of mass that is consumed in the system. If it is an energy balance, then it is rate of accumulation of heat and thermal energy is equal to rate of energy thermal energy going into the system minus going out of the system. If there is some source term, it will be generated, rate of generation should be included in a governing equation. If it is a dissipative system, then you have to write a rate of consumption term in a governing equation. So, in our case the material, that is the rate of accumulation will be existing and rate of going into the system. So, the material, the reactant that is going into the system, that is there, going out of the system, that is there, but there is no rate of generation of the reactant that is there in your system, but the reactant is continually consumed because of the reaction. So, rate of generation term will not be there and rate of consumption term will be there, but since we are talking about a steady state operation, then rate of accumulation, which is time dependent part, it will be not there, because at the steady state is basically time independent portion of the profile of the operation. So, therefore, if you write the balance equation, so it becomes rate of material that is going into the system is Q times Cf. Q is the volumetric flow rate. So, it has a unit of meter cube per second, and Cf has a unit of concentration, that is kg per meter cube. So, Q times Cf is has a unit kg per unit time. So, that is the rate of material of the substrate or the reactant that is going into the system minus Q times C is the concentration of the reactant that is coming out of the system. And interestingly, in case of CSTR, the same concentration is existing into the reactor itself. So, that is the material that is going into the system, that is the material that is coming out of the system. There is no generation of the reactant. On the other hand, reactant is basically getting consumed. So, this will be minus Ra times V. So, that will be equal to 0. So, this is the rate expression, the mass balance equation for the species in this particular problem. Now, what we are going to do? We are going to substitute the expression of minus Ra by the Monod's kinetic given in this problem. So, this becomes Q times Cf minus Q times C minus K1 C divided by 1 plus K2 times C multiplied by V should be equal to 0. Then we divide both sides by Q. So, Cf minus C is equal to K1 V over Q C divided by 1 plus K2 C. Now, we make the concentration non-dimensional by C by Cf, and we call this quantity as non-dimensional concentration X. So, this X is nothing but a non-dimensional concentration, and this concentration is non-dimensionalized with respect to fit concentration. So, this will be 1 minus X minus K1 V over Q times X divided by 1 plus, we make this also non-dimensional. So, this will be K2 times Cf multiplied by X. So, if you look into this equation, the first term is non-dimensional, the second term is non-dimensional, and third term it will be constituting of two parts, numerator and the denominator. If you look into the dimension of K1 V and Q, so V by Q is nothing but a unit of second, and Q1 will be having a unit of second inverse. So, this will be non-dimensional, X is non-dimensional. So, therefore, the denominator has to be non-dimensional, that means K2 times Cf, which will be having a unit of concentration inverse. So, K2 times Cf will be again a non-dimensional quantity. So, therefore, the parameters of this equation automatically comes out from the non-dimensionalization of the governing equation. That is, in fact, that is the aim of the first part of this question. You have to evaluate, we do not know what are the non-dimensional parameters of a particular system, of a mathematical model that will be representing a particular chemical engineering system. So, first of all, you have to make it non-dimensional. During the non-dimensionalization of the equation, some of the parameters will be coming out automatically, and these are the typical non-dimensional operating or non-dimensional parameters, which are basically combination of the operating conditions which will be relevant for this particular system. So, this is the method to identify the non-dimensional operating conditions or the non-dimensional parameters in a typical chemical engineering process. So, we write down the non-dimensional parameters as Damkohler number equal to K1 V over Q and sigma is equal to K2 times Cf. So, let us write down the whole equation in its non-dimensional form. 1 minus X minus dA times X divided by 1 plus sigma X is equal to 0. Now, then what we will do, we rearrange this equation. This is therefore, this is the governing equation, and since it is an isothermal operation, okay, this is the governing equation that mathematically represents this chemical engineering process. That is the isothermal enzyme catalyzed fermentation process. But since this process is isothermal, we need not to write the heat balance equation. There is no need to write down the heat balance equation. So, we recast this governing equation in the form X is equal to f of X. But we have to remember the as we have seen in the last class, the casting of this equation is of extremely importance, so that you will be getting the domain on the domain of parameter on the left hand side must be the domain of the parameter in the right hand side. For example, if X lies in the domain 0 to 1, Fx, the right hand side, should also lies in the domain 0 to 1. If X lies in the 0 to 1 and if Fx lies in the domain 0 to infinity, then the choice or rearrangement of this form x is equal to f x is not appropriate. So, what is the appropriate form of x is equal to f x? Both the domain of left hand side and right hand side should be identical. So, therefore, we recast this equation in this form. We take 1 to the other side. So, it will be x 1 plus dA divided by 1 plus sigma x is equal to 1. So, 1 plus sigma x 1 plus dA plus sigma x should be is equal to 1. So, x becomes 1 plus sigma x divided by 1 plus dA plus sigma x. So, this is the form x equal to f x for this particular problem. Now, if you see the range, the domain of the parameters of the variable, the left hand side, what is x? X is nothing but C by Cf. So, the maximum concentration of C should be Cf and the minimum should be 0. So, x must be lying in the domain 0 to 1. Now, if you look into the parameters sigma and dA, both sigma and dA can be assuming any value in the domain 0 to infinity. So, that is a generalized domain. Typically, they are all positive, sigma and dA both are positive, and depending on the parameters k1, k2, v and q, they will be assuming some values. So, generally we can say that sigma and dA must be lying in the positive right half plane of the real axis. So, therefore, sigma and dA can be assuming any value. So, if that is the case, if you look into the numerator, this is 1 plus sigma, and on the other hand, if you look into the denominator, this is 1 plus sigma, the numerator is 1 plus sigma x, the denominator is 1 plus sigma x plus dA, some amount of positive real number. So, therefore, this will be the numerator, the denominator will be always greater than numerator. Whatever the value of x is or sigma and dA is, the numerator is always less than denominator. If that is the case, f x will be a fraction always. So, that means right hand side is also lying between domain 0 to 1. So, therefore, this is an appropriate choice of x is equal to f x, and this choice is very important as we have seen in the last class. So, otherwise you will be landing up with a wrong result. Okay. Now, let us we have identified what f x is. So, f x is 1 plus sigma x divided by 1 plus dA plus sigma x. So, what we do now, we if you look into the definition of contraction map, it said that metric between the functions f u and f v should be is equal to f prime w, metric between u and v, and this f prime w, if you call this as z, which is a function of a continuous variable w, z is a function of a continuous variable w lying in the domain, same domain 0 to 1. It is lying in the same domain of x, the original variable. This map, then f is a contraction map if maximum value of z should be less than 1. So, then f will be depicting a contraction map. So, why, since it is we are assuming the maximum value of z is less than 1, that means any value of z below the maximum value will be will be basically less than 1. So, maximum value z max less than 1 condition ensures that any value of z will be less than 1 and it will be a fraction, and this f will be a contraction map. So, that is the idea. So, therefore, we first evaluate f prime x. F prime x is nothing but d dx of f x. So, it will be 1 plus sigma x 1 plus dA plus sigma x. So, we use the first function, differentiation of the first function, and then differentiation of the second function. So, we take the numerator as the first one and denominator as the second one. So, we differentiate the numerator first in the first step. So, it will be sigma 1 plus dA plus sigma x. Next, we keep this as fixed 1 plus sigma x and differentiate 1 over 1 plus dA sigma x. So, since it is inverse, so there will be minus sign here. So, it will be minus there multiplied by 1 plus dA plus sigma x square of that, and since sigma x is there, one more sigma will be coming out of it. So, that is the sigma divided by 1 plus dA plus sigma x whole square is the ddx differentiation of 1 over 1 plus dA plus sigma x. So, we simplify this equation. So, we can take sigma divided by 1 plus dA plus sigma x common. So, this will be 1 minus 1 plus sigma x divided by 1 plus dA plus sigma x bracket. So, this will be, if it is simplified, 1 plus sigma x will be cancelled out, and what is left behind is dA only. So, this will be sigma times dA divided by 1 plus dA plus sigma x square. So, now we have evaluated f prime x. So, next we evaluate f prime x at x is equal to w. So, f prime x is evaluated at x is equal to w. W is somewhere in between the domain of x, that is from 0 to 1. So, therefore, this becomes sigma dA divided by 1 plus dA plus sigma w square. Okay. Now, if you see that what is the implication of this is that so f prime x evaluated at x equal to w should be equal to z, and we have talked about earlier, and z is a function of continuous variable w lying in the domain 0 to 1. So, therefore, we look into the as you remember that the next step is that we look into the maximum value of z max. So, z will be maximum under what condition. So, that is our next step, since w maximum is equal to 1 and w minimum is equal to 0. So, therefore, if we put, and since w is appearing only in the denominator of the expression of z, if you put the maximum value of w here, it will be giving you the minimum value of z. If you put minimum value of w in the denominator, since it is appearing in the denominator, it will give you the maximum value of z. So, z maximum will be obtained when we put the w as the minimum value at its minimum value. What is the minimum value of w? Minimum value of w will be equal to 0. So, therefore, z max will be sigma dA. We put w is equal to 0. So, therefore, this becomes 1 plus dA whole square. Okay. Now, we have already seen the condition of contraction mapping now. So, what is the condition for contraction mapping? For f to be a contraction map, the Z max should be less than 1. Okay. So, we put Z max to be less than 1, therefore, sigma dA 1 plus dA square should be less than 1. So, we simplify this equation and see what we get. If we really simplify that equation, we will be getting sigma dA divided by 1 plus dA square of that less than 1. So, therefore, sigma dA should be less than 1 plus dA square. So, this will be equal to 1 plus 2 dA plus dA square. So, therefore, this will be dA square plus dA 2 minus sigma plus 1 should be greater than 0. So, you are going to get this equation. So, sigma is typically a value above in the positive domain. So, we can write it as minus sigma minus 2 plus 1 greater than 0. Now, we like to let us try to solve this equation in terms of dA. So, it has become a quadratic in dA. So, therefore, what we do a mathematical analysis of this equation and see what we get. So, dA square minus 2 times dA times sigma minus 2. So, we multiply and divide by 2 and add sigma minus 2 divided by 2 square and subtract sigma minus 2 divided by 2 square. 1 is there, keep the 1 should be greater than 0. We are trying to make a perfect square out of it. So, therefore, we will be getting dA minus these, considering these 3 terms, dA minus sigma minus 2 by 2 whole square should be greater than sigma minus 2 by 2 square minus 1. Now, we have a perfect square on the left hand side and in the form y square minus m square in the right hand side. Just take the square root, you will be getting dA minus sigma by 2 sigma minus 2 by 2 should be plus minus root over sigma minus 2 by 2 square minus 1. So, you can say you can take sigma term on the right hand side and come to the conclusion that dA should be greater than sigma minus 2 by 2 plus minus simplify this equation. This will be 4 coming out of the root, it will be 2. So, this will be sigma minus 2 whole square minus 4. So, if you simplify this equation, this minus sigma, this will be sigma minus 2 by 2 plus minus sigma square minus 4 sigma plus 4 minus 4, this plus 4 minus 4 they will be cancelled out and you will be getting a very simple and amenable form of dA, and then dA becomes greater than 0.5 sigma minus 2 plus minus under root sigma square minus 4 sigma. So, this is the condition, one of the conditions on the parameters dA and sigma should satisfy in order to have a unique steady state on this particular problem. Similarly, if you would like to have for a real solution of the system, for a real solution sigma, the term within the under root, it has to be positive, otherwise it will be an imaginary value. So, therefore, another condition is sigma square minus 4 sigma should be greater than 0. So, sigma, so this has a
solution of this will be sigma into sigma minus 4 is greater than 0, sigma should be greater than 0, but sigma is always greater than 0, that will not give you any other interpretation. So, the limiting condition is sigma minus 4 should be positive. So, sigma minus 4 should be positive, that means sigma should be greater than 4. So, we get a bound on sigma, and in general the maximum sigma is lying between we said from it is lying on the positive real half plane up to infinity. So, therefore, we can identify the domain of sigma. The minimum value of sigma should be 4 and the maximum value is infinity. So, sigma must be lying in the domain 4 to infinity. So, sigma lying in between 4 to infinity, and we have obtained that. So, what is the so these two are the condition on the parameters. So, what are the condition of the parameters? The condition of the parameters is sigma has to be greater than 4 and Damkohler number should be satisfying this equation in order to have a unique steady state to this particular problem. So, what is the minimum value of Damkohler number? If we put the value sigma is equal to 4 there, we will be getting the minimum value of Damkohler number. So, Damkohler minimum will be turning out to be 0.5 into 2. So, that will be equal to 1. So, this is a very interesting and typical application of contraction mapping, and we have seen that how contraction mapping can be utilized in case of enzyme catalyzed fermentation process, and in order to obtain a unique steady state for this particular system, what will be the conditions on the parameter we have to think of. So, we move to the next illustrative example. So, next example of today's class is again a we consider an enzymatic catalyzed reaction. And again the kinetics is governed by Monod's kinetics, that is minus R of A is equal to K1 C divided by 1 plus K2 times C. We have again the reaction is occurring in a CSTR with volume V, flow rate Q, and feed concentration of reactant CF, and again we are considering an isothermal irreversible reaction. Reactant gives the product, and we have solved in the last problem, as this is the governing equation of the reaction of the Monod's kinetic, but in this problem it will be slightly changed. This will be K1 minus RA is equal to K1 C divided by 1 plus K2 C whole square. So, the only difference in this problem is almost is identical of the previous problem, but the Monod kinetics is different. So, my intention is, if we have the different kinetic rate of reaction, then what will be the typical bounds or the conditions on the operating variables, so that you will be getting the unique steady state for a particular system. Now, by changing keeping everything fixed, keeping all the parameters fixed, by changing the reaction kinetics, see how the the relationship between the parameters will evolve in order to have a unique steady state in your particular example or particular system. So, therefore, we again in this problem the solution goes like this. Since it is isothermal, no need to write down the energy balance equation. It must be mentioned here that I will be taking very simple problems to illustrate the principles, but actually the problems may be quite complicated and the whole system may be non-isothermal, then the equations may not be solved analytically in the class. So, one has to take recourse to the numerical techniques. So, that thing must be kept in mind. So, we will be solving very simplified problem and trying to illustrate the principle and how the solution changes by using the contraction mapping. So, we write down the mass balance equation under the steady state. The species balance equation, or that means basically the reactant balance equation. So, this becomes Q times Cf minus Q times C minus K1 C times V divided by 1 plus K2 C whole square should be is equal to 0. So, again the same principle, rate of accumulation is 0, Q times Cf is the reactant coming into the system, Q times C is the amount of reactant that is going out of the system per unit time minus the reactant that is consumed in the throughout the whole volume of the system. So, rate of reaction must be multiplied by the volume of the reactor. So, we will be getting this equation. So, again we will be doing the same thing, we make the whole system non-dimensional, and if you make the whole system non-dimensional, the following non-dimensional parameters will be evolving out of it. So, we write C by Cf as x, that is the non-dimensional concentration, divide the whole equation by Q. So, you will be getting Cf minus C minus K1 V divided by Q times C 1 plus K2C square of that is equal to 0. Again divide by Cf. So, you will be getting 1 minus x minus K1 V over Q times C by Cf. So, that will be x 1 plus K2x square of that. So, in this particular so this should be K2 times Cf, we multiply and divide by Cf, there will be a Cf here. So, we have the evolution of the non-dimensional parameters, K1 V by Q is nothing but Coulomb number, K2 times Cf is nothing but sigma, that whatever we have described earlier. So, okay, there is a mistake here, this is if you divide by Cf, this becomes 1 minus C by Cf. So, it will be x, not 1 over x. So, this will be x only. Okay. So, we rearrange this equation to cast it in the form of x is equal to f x. So, x plus Coulomb times x divided by 1 plus sigma x square is equal to 1. So, take x common. So, it becomes 1 plus sigma x whole square Coulomb plus 1 plus sigma x square bracket n is equal to 1. So, take the third bracket on the right hand side. So, this becomes 1 plus sigma x square divided by dA plus 1 plus sigma x whole square. So, this is the form x is equal to f x, and we identify this is f x. So, as we have seen earlier that x lies in the domain 0 to 1. So, in this domain whatever the value of x, if you look into, if you put the, you can check it for x is equal to 0, that is the minimum value of x. What is the value of f x? For x equal to 0, this will be 1 divided by dA plus 1. For x is equal to 1, what is the value of f x at x is equal to 1? This will be 1 plus sigma divided by dA plus 1 plus sigma. Since the parameters dA and sigma are extremely high, so they are all real positive. So, in this case 1 over dA plus 1, so it will be always less than 1. In this case this is 1 plus sigma divided by dA plus 1 plus sigma. So, denominator is always greater than numerator. So, this will be always less than 1. So, in this case as well f of x lying in the domain 0 to 1. So, we have selected an appropriate map x equal to f x, and this has every quality to be qualified as a contraction map. Okay. Next, we will, if you remember the so the f choice of f x is appropriate, and it can be a well behaved contraction map. In order to just find out the next of the steps, if you remember, the next step is we find out f prime w, okay, and we mark it as z. Then we have to check that whether the maximum value of z, if the maximum value of z should be less than 1, so that f is a contraction map. So, we write, so we follow the steps. First we evaluate f prime x, in at x equal to w, where w is a variable lying in the same domain of x 0 to 1. Then we evaluate z maximum and put z maximum less than 1. So, therefore, first we find out what is f prime x, 1 plus sigma x square divided by dA plus 1 plus sigma x square. So, what is f prime x? Again we, this numerator is as one function and denominator as the second function. So, it will be 2 sigma 1 plus sigma x, that is the differentiation of the numerator. Denominator remains as it is. Then we evaluate the we differentiate the denominator. So, 1 plus sigma x square remain as it is, the whole thing raised to the minus 1. So, on differentiation there will be minus sign here, then differentiation of this. So, this will be, this is constant, no contribution from this term. So, from this term there will be contribution, 2 comes from there, sigma comes from here, 1 plus sigma x, and then denominator becomes a square. So, 1 plus sigma x square of that. Now, let us simplify this equation. Take 2 sigma 1 plus sigma x divided by dA plus 1 plus sigma x square common. So, it will be 1 minus 1 plus sigma x square divided by dA plus 1 plus sigma x square of that. one thing has taken. So, this square out of these two, the power 2, there will be only one that is left behind. So, on simplification, 1 plus sigma x whole square in the numerator will be cancelled out. So, what we will be getting only as 2 sigma dA 1 plus sigma x divided by dA plus 1 plus sigma x square of that, then whole square. So, that gives the expression of f prime x. Next, we evaluate f prime x at x is equal to w. So, we evaluate that f prime x evaluated at x is equal to w, and we call that as z, and this becomes 2 sigma dA 1 plus sigma w divided by dA plus 1 plus sigma w square of that. Now, if you remember that we have utilized, we have already seen that what is the value of w. W is again in a running variable. It is a variable in the lying in the same domain of x from 0 to 1. So, therefore, z is a continuous function of w. So, in order to have this z to be less than 1, we should consider what is the maximum value of z. If that is less than 1, then all the values will be less than 1. So, next we evaluate z max to be evaluated. How z max will be evaluated? Z max will be evaluated, since z is a continuous function of w, we use dz dw is equal to 0, and we evaluate dz dw and put it equal to 0. That will give you the maximum value of z. If you do that, so it will be is equal to 2 sigma dA times sigma dA plus 1 plus sigma w square of that, minus one more differentiation for the denominator. The numerator remains constant. So, 2 sigma dA 1 plus sigma w, that is present there. Next, we will be getting 2 times 2 sigma, and one more 1 plus sigma w will be coming. So, this will be, there will be square of that divided by dA plus 1 plus sigma w square. Since there is a when it is you are differentiating, this will be minus 2. So, after differentiation it will be minus 3. So, it will be denominator, it will be cube. So, we put it equal to 0. So, after doing all this simplification, I am just omitting one more step and writing the expression 4 into 1 plus sigma w square divided by dA plus 1 plus sigma w square. So, therefore, we will be getting this equation 1 plus the equation that we will be getting 1 plus sigma w square multiplied by 3 is equal to Damkohler number. So, 1 plus sigma w square will be dA by 3. So, at this value of 1 plus sigma w whole square, it becomes dA by 3. So, 1 plus sigma w is nothing but dA by 3 under root. So, here at this condition the z becomes maximum. So, what is the value of z max? Maximum value of z is that wherever in the expression of z we have 1 plus sigma w, going to replace it by root over dA by 3. So, if that is the case, so this becomes 2 sigma dA root over dA by 3 divided by dA plus 1 plus sigma w whole square. So, it will be dA by 3 square of that. So, what we will be getting is that 2 sigma dA root over dA by 3 multiplied by, this will be 3 plus 1. So, it will be 4 by 3. So, 9 by 16 dA square in the denominator. So, 1 dA will be cancelling out. So, it will be 2 8. So, 9 by 8 root 3 sigma by root over dA. So, 1 dA will be here, root over dA there, sigma by root over dA. So, this becomes so you will be having a square there. So, that is fine. Okay. This 9 is there. So, this will be 9 by 8 by root 3 sigma by root over dA. Now, for contraction mapping, our condition is that Z max should be less than 1. So, therefore, sigma by root over dA should be less than 8 root 3 divided by 9. So, this is the condition of contraction map. This is the condition for this particular problem, where we will be having a existence of unique steady state. So, root 3 is around 1.732. So, this value will be 8 into 1.732, it will be around a value around 14 divided by 9. So, it will be around 0.7, 0.8. So, sigma by root over dA should be less than should be less than 0.8 or so. So, that is the condition of the operating variables sigma and dA should satisfy in order to have a unique steady state for this particular problem. So, again this example demonstrates how the contraction mapping would be utilized to find out the unique steady state in any chemical engineering system. So, we stop here. In the next class, we will be taking up one more example of contraction mapping. So, the calculations and the procedure becomes absolutely clear to all of you, and then we will move to the next topic. Thank you very much.